In activity 13, we are told that fx is divisible by x plus 2 and that when fx is divided by x minus 3, it gives a remainder of 30. In the first question, we have to determine the values of p and q, so therefore we'll need two equations that we can solve simultaneously. Now, from the piece of information that f of x is divisible by x plus 2. When something is divisible by x plus 2, it means it can be divided with a remainder of 0, which means that x plus 2 is a factor of fx, and therefore f of negative 2 is equal to 0. Then we're also told that when fx is divided by x minus 3, it gives a remainder of 30. So from that information, we can write down that f of 3 is equal to 30. So if I now calculate f of negative 2 and equate that to 0 and get this equation in its simplest form, it will give me the equation that 2p plus q is equal to 1. If we expand f of 3 equals 30 and simplify our equation, we will get that 3p minus q is equal to negative 1. We can easily solve these two equations simultaneously by adding equation 1 to equation 2. So when we add equation 1 to equation 2, we get 5p is equal to 0, which implies that p is 0. If I now substitute p equals 0 into equation 1, it gives me that q is equal to 1. In activity 13.2, we are now asked to factorize fx over r. From activity 1, we know that p is 0 and q is 1, so that means fx is x cubed minus x plus 6. From the given information, we already know also that x plus 2 is one of the factors of fx, and we can find other factors by doing long division with x plus 2. So if I divide x plus 2 into x cubed plus 0x squared minus x plus 6, my quotient is x squared minus 2x plus 3, and it gives me a remainder of 0. Now, this remainder of 0 was to be expected because we already know that x plus 2 is a factor. So also the fact that our remainder is 0 confirms that my p and my q value is probably correct. If you do your long division with something that you believe is a factor and you do not get a 0 as the remainder, you might have made a mistake in your long division, but it also might mean that you made a mistake when you calculated your p and your q value. Another alternative is to do the factorizing by inspection, but inspection will not confirm for us that our p and our q value is correct. So we can now write f as a product of the divisor times the quotient plus the remainder, but the remainder is 0, so fx can be factorized as x plus 2, x squared minus 2x plus 3. If we now try to further factorize x squared minus 2x plus 3, we see that the discriminant of this bracket is equal to negative 8, which means that x squared minus 2x plus 3 cannot be factorized over the real number system, and my final answer is x plus 2, x squared minus 2x plus 3. However, in activity 13.3, we are asked to factorize fx over the complex numbers. So we already know that fx is factorized as x plus 2, x squared minus 2x plus 3. Since x plus 2 is linear, that is a real factor, and we will not factorize that over the complex numbers. But x squared minus 2x plus 3 is a quadratic factor, and we need to factorize that factor over c. Now, the easiest way to do this is by first completing the square. So if I look at my x term, minus 2x, half of minus 2 is 1, so I have to add 1 squared and subtract 1. So when I complete my square, x squared minus 2x plus 1 is x minus 1 squared, and negative 1 plus 3 gives me 2. Now, this bracket is now being written as the sum of two squares. And the problem is we know that the sum of two squares cannot be factorized over the real number system. So what we're going to do is we're going to use the fact that I squared is equal to negative 1 and rewrite plus 2 as negative 2i squared. So what we have done now is we've written that last bracket as the difference of two squares, which we can factorize. So if we factorize the difference of two squares, it will give me two brackets, one with a plus, one with a minus. The first term in each bracket will be a x minus 1, and the last term in each bracket will be a square root 2i. And now fx has been factorized over the complex number system. So there's one real factor and two complex factors. In activity 14, we are shown the graph of fx, where fx is divisible by x minus 1, and when fx is divided by x minus 2, it gives a remainder of negative 4. We are asked to indicate the given information on the figure, but before we do that, we first have to interpret the given information. So when we're told that fx is divisible by x minus 1, of course it means that x minus 1 is a factor of fx and that f of 1 is 0. When fx is divided by x minus 2, it gives a remainder of negative 4, can be interpreted as f of 2 is equal to negative 4. Now, if x minus 1 is a factor of fx, it means that 1 is an x-intercept of fx. Now, if I look at my graph, I see that there are two positive x-intercepts. So if I take a guess that my first intercept is 1, and then take the piece of information that f of 2 is equal to negative 4, then 2 is somewhere here, and then f of 2 must be negative 4, will be interpreted as shown on the graph. If I try to make b equal to 1, then the given information wouldn't have worked, because then f of 2 would have had to be positive, and that wouldn't match the information that f of 2 is negative 4. So I'm quite confident that I've got the 1 on the correct place. The x-intercept of 1 is correctly placed. In 14.2, we now asked to determine m and n. If we use the fact that f of 1 is equal to 0, calculate f of 1 and equate it to 0, it gives me the equation that n plus m is 4. If we take that f of 2 is negative 4, and evaluate f of 2 and equate it to minus 4, we get that 4n plus m is equal to negative 2. These two equations can easily be solved simultaneously by subtracting them from each other. So if I take equation 2 minus equation 1, it gives me that 3n is equal to negative 6, which implies that n is negative 2. If I now substitute n equal negative 2 into equation 1, it will give me that m is equal to 6. In 14.3, we're asked to determine the other x-intercepts of fx. Now we know that n is negative 2 and m is 6, and when we calculate x-intercepts, we let fx equal 0. So we have to factorize the x cubed minus 2x squared minus 5x plus 6. We already know that x minus 1 is one of the factors of this equation, and you can find the other factor either by inspection or by long division. So my other factor would be x squared minus x minus 6. X squared minus x minus 6 can be further factorized as x minus 3 x plus 2, which gives me the three x-intercepts that x is 1, or x is 3, or x is negative 2. So if I look at my graph, we already knew the x-intercept of x equal 1. If I now look at the x-intercept equal x equals 3, it makes perfect sense that b is equal to 3 and that a is therefore equal to negative 2. In activity 14.4, we now asked to evaluate the integral of fx over the interval a to b. Now we've just calculated in activity 14.3 that a is negative 2 and that b is equal to 3 and that the other x-intercept over here is of course equal to 1. So basically, it means that we have to integrate fx over the interval minus 2 to 3, which we can easily do with the power rule. And if we then evaluate this function between the values negative 2 and 3, it gives me an answer of 10.42. You can go to GeoGebra and you can type in this function x cubed minus 2x squared minus 5x plus 6 into GeoGebra and then use the integral command to integrate this function on the interval minus 2 to 3 to confirm this answer of 10.42. In activity 14.5, we're asked to evaluate the integral of the absolute value of fx over the interval minus 2 to 3. Now, if we look at the interval from minus 2 to 3, we realize that on parts of that interval, f is positive, but on other parts it's negative. So if we do the absolute value, the negative parts must become positive. And that means that we have to divide this integral into two intervals. So the first interval will go from minus 2 to 1, where we use fx, and the second interval will go from 1 to 3, but on that interval we will be using negative fx. So again, we can integrate both these integrals with the power rule, and if we now determine the values, if we substitute the values and simplify, we get a final answer of 21.08. In activity 15, we are given an equation 9x minus 21 over x cubed minus bx squared minus x plus q is equal to a over x minus 1 plus b over x minus 4 plus c over x plus d. Now, if you see, there are actually 6 unknowns in this equation, and that's the only information they've given us. In 15.1, we are asked to determine the values of p and q. So, what can we do to determine the values of p and q? Well, if we look at our fraction and we therefore assume that we can decompose the fraction 9x minus 21 over x cubed minus bx squared minus x plus q into the three fractions a over x minus 1, b over x minus 4, and c over x plus d, it implies that x minus 1 and x minus 4 are factors of x cubed minus bx squared minus x plus q. Since x minus 1 is a factor, I can assume that d of 1 is 0, and since x minus 4 is a factor, I can assume that d of 4 is 0. Using this information, I can get equation 1, which is minus p plus q is 0, and equation 2, which is negative 16p plus q is negative 60. I can now solve these two simultaneously by subtracting the two equations. So if I take equation 1 minus equation 2, it will give me that 15p equals 60, and therefore p is equal to 4. Equation 1 will give me that p is equal to q, and therefore q must also equal 4. Now we're asked to determine the value of d. So we already know that our denominator is x cubed minus 4x squared minus x plus 4, And we also already know that we have factors x minus 1 and x minus 4. So we can very easily determine the last factor by inspection, which will give us x plus 1. And that means that the value of D is equal to 1. In activity 15.3, we now asked to calculate the values of A, B, and C. So from the previous two activities, we can rewrite our equation as 9x minus 21 over x cubed minus 4x squared minus x plus 4 is equal to A over x minus 1 plus B over x minus 4 plus C over x plus 1. So to find the values of A, B, and C, we need to do partial fractions. If we multiply our equation both sides by the LCD, which is x minus 1, x minus 4, x plus 1, we will get that 9x minus 21 is equal to A, x minus 4, x plus 1, plus B, x minus 1, x plus 1, plus C, x minus 1, x minus 4. Since we have all linear factors, it will be easiest to find the values of A, B, and C by choosing our x values as as 1, as 4, and as minus 1. So if I let x equal 1, then the B term and the C term will become 0. And if I substitute 1 on the left-hand side, it will give me a negative 12. If I substitute it on the right-hand side, it will give me that negative 6a. So from that, I can determine that a is equal to 2. If I now let x equal 4 and substitute that on my left-hand side, it will give me 15. 36 minus 21 is 15. And if I substitute it on the right-hand side, the a term and the c term will become 0, and I will end up with a 15b, which implies that b is equal to 1. If I now lastly let x equal negative 1, then negative 9 minus 21 is negative 30 on the left-hand side. My a term and my b term will become 0, and my c term will give me a 10c, which implies that c is negative 3. So I've now calculated the values of a, b, and c. As the last question, we're asked to evaluate the integral of 9x minus 21 over x cubed minus bx squared minus x plus q. So from activity 15.3, we know that this integral can be written as the integral of 2 over x minus 1 plus 1 over x minus 4 plus negative 3 over x plus 1, which is easy to integrate as all three of those terms will integrate as ln. And my final answer is 2 ln of absolute x minus 1 plus ln of absolute x minus 4 minus 3 ln absolute x plus 1 plus c. And we're done.